Welcome to this explainer. If you're just stepping into the world of computer engineering, maybe starting your Week 1 Foundations of Computer Programming class, you've probably been hearing a whole lot about coding, algorithms, and software. But today, we're going to do something a little different. We are going to totally strip away the magic of programming. We're going right back to the very foundation, looking at the actual physical reality of what a computer is and how it mechanically processes the very thoughts you type into your keyboard.
It's a pretty wild question when you really stop and think about it, isn't it? What exactly happens when you type a line of code, you hit run, and somehow text on a screen miraculously translates into a character jumping in a video game or a ridiculously complex math problem getting solved in just milliseconds? Well, to truly master programming, you can't just memorize syntax. You really need to travel down from that high-level software all the way down to the microscopic physical hardware level. You need to intimately understand the machine you're actually commanding.
Okay, let's dive into this. Here is our blueprint for today. First, we'll look at the layers of hardware abstraction. Second, we're going inside the CPU brain. And third, we'll map out the memory hierarchy.
So, Part 1. The hardware abstraction layer.
To really wrap your head around this layer, try visualizing a computer not as a flat, boring box, but as a towering building. As a programmer writing code, you absolutely do not want to be thinking about exactly which microscopic transistor is turning on down in the basement, or which specific circuit on the graphics card is firing at any given millisecond. I mean, that would just be impossible to manage. This is where this incredibly magical concept called abstraction comes in. It's essentially an illusion that completely hides all those complex low-level hardware details. And it does this to provide a clean, standard, and perfectly safe workspace for your software. You don't need to manually flip physical switches because the abstraction layer handles all of that translation for you. Imagine you're stepping into an elevator in this massive building. Down in the basement, that's step 1. We have the foundation. This is the physical hardware, the logic gates, the microarchitecture, the literal data buses and pipelines. Now, moving up to step 2, we hit the bridge, which we'll actually talk about more in just a second. Step 3, well, that's the utility room. This houses the operating system's kernel and drivers. This is really the heart of the whole abstraction process. No matter what brand of keyboard or hard drive you plug in, the kernel ensures the operating system speaks a completely standard language to it. And finally, way up at step 4, we have the penthouse. This is your operating system APIs and your applications. This is where your user software lives, perfectly insulated and completely safe from all the chaotic electrical engineering happening down in the basement.
Let's actually pause and look a bit closer at that bridge on floor 2, the Instruction Set Architecture, or ISA for short. Honestly, this is arguably the single most important concept for an engineering student to grasp. The ISA is the official border crossing between hardware and software. It literally defines the exact vocabulary of hard, electronic commands that the processor can directly understand, basic commands like add or jump. It is the ultimate translator. Every single high-level program you will ever write eventually boils down to the strict rules set by this ISA.
All right, moving on to part 2, inside the CPU brain.
So let's take a trip right down into the engine room. We always hear the central processing unit, the CPU, called the brain of the computer. But, as engineers, we really need to challenge that analogy. A brain implies free will, right, or creative thought. But technically speaking, a CPU is just a relentless, highly structured mechanical machine. It's really just a massive timer and a command executor state machine. It has absolutely no mind of its own. It only does exactly what it's told over and over and over again. To pull this off, the CPU is basically split into 3 main logical parts. First up, the ALU, which stands for Arithmetic Logic Unit. This is where all the physical math, your addition, your multiplication, and all the logical comparisons, like checking if one number is greater than another, actually happen using real electronic gates. Next is the control unit. You can think of this one as the orchestra conductor. And finally, we have registers. These are ultra-fast memory cells housed right inside the processor itself. To give you an idea of their scale, they usually hold just 32-bit or 64-bit values, but they operate at blazing sub-nanosecond speeds. Now, what's really interesting about this whole setup is the rhythm of that conductor, the control unit. It runs this never-ending 3-step waltz. Step 1 is fetch. It grabs the next instruction right out of memory. Step 2 is decode. It figures out what the command actually means. And step 3 is execute. It generates the exact electrical signals needed to make the ALU or other parts of the system actually do the work.
And here's the crazy part. The CPU repeats this fetch, decode, execute cycle literally billions of times every single second, completely dictated by its clock speed. With billions of cycles happening so fast, you might be wondering, how does it not just get lost? Well, the CPU relies on two very specific registers to keep its place. The program counter, or PC, acts kind of like a bookmark. It holds the exact address of the next instruction that needs to be fetched. Meanwhile, the instruction register, or IR, safely holds the current command that is being executed right at that moment. Working together, these two ensure the CPU flawlessly keeps its place in your code, executing line by line without ever skipping a beat.
Okay, part 3, the memory hierarchy. So we've got this incredibly fast engine, but, an engine needs fuel. Let's move our discussion over to the storage warehouses. In computer architecture, the absolute dream is simple. Ideal memory would have totally infinite capacity, cost absolutely nothing to make, and operate at the speed of light. Sounds great, right? Unfortunately, physics and basic economics kind of get in the way. It is physically and financially impossible to build one single type of memory that does all of that. So, reality requires a hierarchy. It's a very careful balancing act between blazing speed and massive capacity. Let's break down this hierarchy using a super simple everyday analogy. A chef working in a kitchen. Up at the very top, we have our registers. These are incredibly fast, but remarkably tiny. This is literally like the ingredients the chef is already holding in their hands right now. Next down is the cache. This includes L1, which is closest to the core, then L2, and the larger shared L3 cache. These are built with expensive SRAM technology to keep the CPU from waiting around. This is like having your ingredients perfectly chopped and prepped sitting right there on the cutting board counter. Further down is RAM, our main memory. It uses DRAM technology, so it's a bit slower but much larger. This is your refrigerator. Finally, way down at the bottom, we have storage. Think of your SSD or a mechanical hard drive. Massive capacity, very cheap to produce, but incredibly slow compared to the CPU. This is basically the grocery store down the street.
Now, there's a really critical distinction here between RAM and storage that we need to talk about. RAM is volatile. That means the second you pull the plug and cut the power, all that data completely vanishes. Storage, on the other hand, like your SSD, is non-volatile. It holds onto your files permanently, power or no power. So the crucial takeaway here is this massive architectural bottleneck. The CPU is so unbelievably fast that it physically cannot and will not talk directly to your slow hard drive. For any piece of data to actually be processed, it first has to be driven all the way from the grocery store, placed in the fridge, moved to the prep counter, and finally put into the chef's hands. Simply put, it must load from storage into RAM before the CPU can even touch it.
And that brings us to part 4, hardware functions summarized.
So, we've traveled from the high-level software layers all the way down to the physical silicon. Think of this summary as the ultimate blueprint for your Week 1 notes in Foundations of Computer Programming. This is the computer completely laid bare. You've got the ALU doing all the heavy mathematical lifting, the control unit brilliantly orchestrating that fetch, decode, execute waltz, the registers holding the immediate right-now data directly inside the chip, the RAM serving as your volatile active workspace, and finally the storage, safely keeping everything totally intact when you turn the power off for the night. Every single piece of hardware perfectly abstracted away, all so you can just sit down and focus on writing great software.
Which brings us to the end of today's explainer. We've officially replaced the magic with mechanics. We've seen the deep foundation, the relentless engine, and the sprawling memory warehouses. So I want to leave you with this final thought. Now that you can truly see the structured, mechanical architecture humming just beneath your screen, how is knowing all of this going to change the way you write your next line of code? Because remember, you aren't just casually typing text anymore. You are directly commanding a magnificent machine. Keep that in the back of your mind, and you are well on your way to truly thinking like a computer engineer.